So the problem that I'm raising is the following. We are given this particular circuit, right? A simple circuit with a voltage source, resistors here, voltage source here, and a current source here. And let us say we have done the analysis. And in red are the node numbers, node number 1 and node number 2 and node number 3 and all that, okay? Next to that is the voltage written here. So let's say we have done the analysis and we have found out that for this source voltage of 1 volt, the output voltage here at this node is minus 14.5. But that's where the design or analysis doesn't end with just one calculation. The person may be interested in knowing, suppose I change VS1 by a small amount. Now, that small amount, maybe there's a ripple in the DC supply here, or it could be due to some temperature variations or whatever. Let's say VS1 changes by 10 millivolt. So VS1 changes by 10 millivolt. And what I would like to know is what would happen to the output voltage here. By how much will the output voltage change? So of course, I have all my nodal or mesh method here. One could go ahead and calculate it again. We have calculated for 1 volt, one can go ahead and calculate for 1.01, and one will have to do a very accurate analysis, keeping all the, as you will see, to the 3rd decimal place here. And because we want to know that because of this change of 10 millivolt here, what is the change in the output voltage here? So I need to calculate this accurately because the change is small here, minus 14.495, and then I can take the difference of the two, and I'll find, well, the output voltage V0 here changes by 5 millivolts. So we could do that. But I'm sure by looking at the problem, you may be realizing that doing the analysis once for 1 volt and doing an analysis again for 1.01 volt, and you have to do the analysis very accurately again to the 3rd decimal place, because if you do it to the 2nd decimal place, you'll get an error. So you have to do it very accurately. Maybe one doesn't need to do this complex approach. And there is a simpler approach. So the point is, you've done the analysis for some voltages and currents that are given in the circuit. And then we are asking, if you change one voltage by a small amount, or if you change the current by a small amount, what would happen to some node voltage, output voltage, or some other node voltage here? That's the question that we are asking. So here, what we are talking about is a concept called incremental circuit analysis. So again, what we are talking about is incremental, and many times the incremental voltage, let's say we are talking about an incremental change in this voltage here. That incremental change many times is a small sinusoidal change here. And that's why this incremental circuit analysis is also called AC analysis, because that small change many times is an AC voltage here, for that reason here. But the proper phrase for this kind of analysis, if you're talking about incremental. So given a circuit like this, what we are saying is the following. This voltage has changed by a small amount, which is same as saying that I've added another voltage source here with an amount equal to whatever was the change here. And so what we are saying, and as a result of this, what would happen is the current which was I1 here will change to I1 plus some small I1, the change here, the incremental change in this current here. This voltage here will change by a small amount, V0 here. This current here will also change to I2 plus I2 here, small I2 here. So incremental circuit analysis means we are looking for is what is this relationship between the change in current I1, the change in voltage, output voltage V0, or the change in this current I2 to the change introduced in the source voltage here. So that's the relationship we are looking at. We are not looking at the relationship between V0 and VS1 or I1 and VS1 and all that. We're looking for these changes here. What happens to the small I1, the change here and the change here and the change here, right? So that's what is meant by incremental circuit analysis. What is the relationship between the incremental change in the source voltage and the corresponding change in the output voltage or some currents that are there here? So we're talking about change in quantities, currents and voltages. So one way of doing it, you may realize that it's a linear circuit. So I can use superposition theorem and calculate what is the effect of VS1. So when we use superposition theorem to calculate the effect of VS1, we'll make this capital VS1 0. It will get shorted here. Current source will become open circuit. VS2 will also become short, and we'll get a simplified circuit, right? But let me build this up from a different angle here. So with VS1, we can write these equations here. VS1 is I1 R1 plus V naught here, and I1 is IS plus V naught minus VS2. So we can write these two equations, and if we solve these two equations, we'll get the answer that we're looking for. Now, let's add this extra voltage here, right? So we add this extra voltage here, so all the currents are changing, voltages are changing here. We can rewrite the equation. We can write VS1 plus small VS1 here. This part here is the same equation, but written with the extra changes that we have introduced. So we'll get these equations here. Now, of course, we can take the difference 3 minus 1 and 4 minus 2. We can take the difference and we can get these equations. So note that incremental circuit analysis, the goal is to find out what are the relationships between the changes in currents and voltages, okay? So we get these equations here. So these equations, if you note, is nothing but tells us the relationship between this change VS1 and the change in current I1 and the change in current V naught here. So it's a set of equations which describe changes in currents and voltages. And if you look at this equation, normally what we do is we start from a circuit and we come to a set of equations, but we can do the reverse also. We can start from equations and go to a circuit. So if we look at these equations, we can map it into a circuit like this. The first equation is VS1 is I1 R1 plus V naught. So here, and I1 is V naught by R2, so it's given by here, right? So we can map it to a circuit like this here. So what we are saying is that the incremental circuit analysis that we had just talked about, relationships between these incremental changes, can be done by solving an incremental equivalent circuit. So from this circuit, we can get this incremental equivalent circuit. And the incremental equivalent circuit, so this is what we just obtained. The incremental equivalent circuit is obtained by replacing each circuit element by its incremental circuit model. Also called, because we are talking about incremental analysis also as an AC analysis, so also called the AC model. Okay, so what we are saying is from this original circuit, we can obtain an incremental equivalent circuit here, where the incremental change in, we are considering only incremental change in VS1. So that is why we have included that here. And how do we obtain this circuit? Well, we use these equations, right? We use this set of equations and this set of equations, and we basically then subtracted them out to get these set of equations here. So what we are saying is that in effect, the incremental equivalent circuit can be obtained by replacing each element by its incremental model. Incremental model meaning incremental model of each element. So you have an element like this, and you'll see that it makes sense that you will arrive at this kind of a thing here. So what do we mean by incremental model of an element? So let's say there is some element, two-terminal element, and it has a relationship between current and voltage described by this manner here. If it's a resistor, then it will be simply I equal to V by R. Now, incremental model of this particular element, any element it can be, would be that if I change my voltage across this particular element by a small amount, let's say V here, then the current would change by a small amount I. And incremental model is nothing but the relationship between these changes, right? So relationship between the small I and the small V here. That's the incremental model here. Okay, so as an example, what is the incremental model of a resistor? So resistor, the equation is V equal to I times R. So let's change the current by a small amount I, as a result of which the voltage across the resistor would change by a small amount V here. And then we can, using these two equations, we can then write small v equal to I times R. So this is the relationship between an incremental change in voltage across the resistor and the incremental change in current through the resistor here. And that relationship is nothing but Ohm's law. So incremental model of a resistor is a resistor of basically the same magnitude. So resistor, when you're building an incremental equivalent circuit, the resistor stays as a resistor. Nothing changes here. Take a capacitor. So capacitor is IC dV by dt. So let's change the voltage by a small amount V here. The current will change by a small amount I. And using these two equations, we can get a relationship between the small incremental change in current and incremental change in voltage. So it's basically the same relationship. So incremental model for capacitor is capacitor of the same magnitude. And the same thing will happen with an inductor also. So they stay as they are. Well, let's take a battery. So when you take a battery, the battery is V equal to constant. Now, if I try to increase, which basically means that the incremental change in this particular one is 0. So if it's a constant voltage source, it means that it cannot change. V equal to 0, which means a battery becomes a short circuit. In the incremental circuit analysis, there cannot be any incremental change in this, or incremental change is 0, and therefore it's like a short circuit. Current source, there cannot be any incremental change in the current, so incremental change in current is 0, which means it's like an open circuit. All right, so with this, we have now a model for all the elements that you see here. So when you want to build an incremental circuit model for this, VS1 has changed by this small amount here. So we'll keep this incremental change here. And VS1 will become short. R1 will remain R1. R2 will remain R2. VS2 will become short. And the current source will become 0. So this is the model that we get. And then this is an incremental equivalent circuit to calculate what is the effect of an incremental change introduced into the circuit here. And then we can get V0 is VS1 R2 by R1 plus R2. Okay, and note that the answer then is obtained very simply here. So this was the equation that this was the example that we were looking at. So if we build an incremental equivalent circuit, it's nothing but R1 and R2 here. With the VS1, the change that we introduced was 10 millivolt, and therefore the answer is 5 millivolts. So the answer is obtained very quickly in a very simple manner. So yes, we could have done it through a superposition kind of a thing, but we have arrived at a similar kind of a analysis through a different route by talking about what is the response of the circuit to an incremental change in some source voltage. And of course, we can extend this analysis to talk about what is the response of the circuit to an incremental change in R1 or incremental change in R2 also. But we'll leave that for a moment. We'll only talk about the response of the circuit only to sources, independent sources that are there in the circuit. Now, this one becomes more interesting as we go towards nonlinear elements. That's where the power of this particular analysis comes in, because for nonlinear elements and nonlinear circuits, we cannot apply superposition theorem, and therefore, we have to rely on. So far, if you would note that we did not invoke anywhere a concept of linearity. All that we have said is an incremental circuit model is the change in current in response to a change in voltage across that particular element. That's all we have said. Okay. So suppose, okay, so I'll skip this for a moment here. Suppose we are given some element, a 3-terminal element like this here. So you can realize that it's a voltage control current source here with the relationship I naught equal to Gm Vi minus V alpha here. And if we are wanting an incremental circuit model for this one, then the procedure is the same. We change the input voltage by a small amount, let's say Vi here. V alpha is a constant. I naught, the current I naught here flowing here will change by an amount small I naught here. And therefore, we are looking for a relationship between small I naught and V naught, which is nothing but I naught equal to Gm Vi. And therefore, we can represent it by this model here. All right, let's go forward. Let's take a more interesting case of a nonlinear element here. Okay, so here is the circuit. This is the incremental change that we have introduced into the circuit. And as I said, often the change, many times the change may be a sinusoidal signal. So that's why we are also calling it a AC analysis in place of incremental analysis here. All right, so this is a circuit here. And this is, let's say there's a nonlinear element here whose current voltage relationship is given as Ix equal to K Vx squared here. So now if you're given a circuit like this, so you've already solved for, let's say, the circuit with a VCC given here. And now we are saying, well, we've introduced this extra change in the circuit. What is the change in V0? So obviously we cannot apply superposition because the circuit is nonlinear because of the presence of nonlinear element. But we can still do incremental circuit analysis by converting it into an incremental equivalent circuit. So the incremental equivalent circuit is built by building the incremental model of all the elements. So we keep this change here, Vs. Battery, because no incremental change in this voltage occurs here, so that's 0. So that's why it becomes a short. Resistor stays a resistor. Current source becomes no incremental change in current, so that is small I equal to 0, so that's why open circuit. And we have to now replace this element by incremental device model here. Okay, and what is the procedure for this? Well, let's change the voltage across this element by a small amount Vx, and then the current will change by a small Ix here. And we are looking for a relationship between small Ix and Vx. Okay, so let's do that here. So we can take this part over there, and this is what we obtain: the relationship between small Ix and small Vx. That of course depends on what is the original value of Vx across the element, right? So the model is nonlinear, right? So the incremental model is the relationship between the incremental change in the voltage across our element X and the corresponding change in the current flowing through the element X. But that relationship, besides being nonlinear, it depends on what was the original bias across that particular element. What was the DC voltage across that particular element? Initial DC voltage here, that's the capital Vx. The other one is the equation is still nonlinear. And nonlinear equations, we have seen that it may require an iterative analysis or graphical analysis. So it makes analysis more complex. And here is where an interesting concept comes in. If the change that we are talking about, incremental change in voltage, let's say Vx, if that incremental change in voltage Vx is small, we can linearize the nonlinear equation. So in this case, note that if this incremental change Vx is much, much smaller than, let's say, the normal bias across this element X, then what we can do is we can do a expansion of this, keep only the first term. We can do 1 plus 2 Vx by here, ignore all the higher order terms. And then the model of this particular element, you can see here, becomes Ix equal to 2k Vx times Vx. So this is the incremental change in voltage across the element X. This is the incremental change in current. And note that 2 is a constant, k is a constant, and Vx is also a constant. Vx is a DC voltage across the element. So when we are talking about incremental changes, that DC voltage across the element is some fixed quantity. Whatever it is, decided by the circuit, but it's a fixed quantity. And therefore, this whole thing is a constant. And we can write it as Ix equal to Vx by Rx. So basically, my element X, under small changes of voltage across it, can be thought of like a resistor. Resistor with a value equal to 1 by 2k times Vx. Right? So what we'll do is, if we wanted to calculate what is the change in V0 here in response to this extra voltage that is introduced here, so we build an incremental equivalent circuit, and now we have seen that this particular element is nothing but a resistor, Rx here, with a value equal to 1 by 2k times V0. V0 would be whatever is the DC voltage across this particular element. So what it is telling you is that before you can do incremental analysis of the circuit, first you have to do the regular analysis of the circuit with the DC voltages and currents. When you do that, you will find DC current here, and you will also find the DC voltage across this particular element here, V0. And that's what we will put here to calculate the value of Rx. And now the analysis is simple. We can calculate V0 is Vs, Rx by capital R plus Rx. So that would be the incremental change in voltage here in correspondence to the change in the voltage that was introduced into the circuit. Right, so the procedure is that take whatever circuit is given here, transform it into an incremental equivalent circuit. And you do that by replacing each element by its incremental model here. Incremental model of the battery, the resistor, the element X, nonlinear element X. And if the changes are small, we can replace all nonlinear elements by linear elements. Okay. All right. So the issue, of course, becomes how small is small. All right. So note that the assumption, if we go back here, the issue was that the incremental change in voltage across the element X should be much smaller than the DC voltage across the element X here. So that depends on how accurate an analysis you want to carry. Depends on how much error you can tolerate. So we had this equation. This was the exact equation, and this is how we approximated it. So we can see, let's say the original DC voltage across the element is 1 volt. And if the incremental change Vx is 0.02, then the error is 1%. If it is 0.22, then it's 10, 0.5, then 21, obviously very, very large error here. So note that if the change in the voltage across the element Vx is small, 0.02, the error is small, and the analysis is fairly reasonable here. And of course, so in this case, if you're looking at, if you can tolerate errors less than 10%, then the change in the voltage across the element X can be as large as 0.22. But then if your nonlinearity is a stronger nonlinearity, in this case, it was a square relationship, quadratic. But suppose I had an element which was Ix equal to K multiplied by Vx to the power 4. And if I did an error analysis again, in this case, I would find this kind of a number. And for less than 10% error, the voltage incremental change in voltage across the element would have been 0.07 here. So I can only under this condition can I really model my element as a linear resistor with respect to incremental changes that are there. All right, so and so it depends on nonlinearity. And one of the strongest nonlinearity that we handle is an exponential. For example, this could be, you may recognize that this may be the diode's characteristics here in the forward bias case here. Vx could be a diode voltage. This is the thermal voltage across a diode, and this is the diode current here. So if we have to build a incremental model of a diode, so a small change in the diode voltage will result in a change in current. We are looking for a relationship between small Ix and Vx here, so we get this here. And then, so it's still nonlinear, and then we are going to build a small signal model, meaning we'll consider Vx to be small. So in this case, you can see here that Vx has to be considerably smaller than 26 millivolt to expand this exponential and keep only the linear term here. So then you will get this particular part here. And in this case, note that again, the relationship between small Ix and Vx is a linear relationship because K is a constant, Vx is a DC voltage, so all this is a constant. And if you would recognize that this is nothing but the DC current flowing through my element X or through the diode here. And so this relationship is still linear. And in this case, if you want to be under 10% error, the voltage across the element should be less than maybe 5 millivolt or so. Okay, so that's the incremental model of it. So note that what we are doing is the following. This is a nonlinear element, just like a diode that we talked about. And we are saying that there is already a DC voltage and a DC current flowing through that element X because of this VCC and R and all that you see here. There is some, so it is, the element X is operating at this particular place here. Now, when we introduce some change in my circuit here, so what would happen is that the voltage across this particular element X is going to change. Let's say if this is sinusoidal here, the voltage across the element X will also change by a small amount here, X here. And as a result of which, the current across the element will also change by a small amount X. So it's that relationship between small Ix and small Vx that we are looking for. That is what we are calling as incremental circuit model. And if the incremental change is, if we keep it very small, we also call it a small signal model. All right, so we'll stop after this. So a general, suppose we have a 3-terminal device. If we have a 3-terminal device like this here, we have seen a 2-port device, a 3-terminal device here. And what we want to do is show you is what would be the incremental or small signal model of such a device here. So we'll take such a device as a unilateral device, meaning that the input current will depend only in the input voltage here, and input current will not be affected by output voltage. On the other hand, the output current will be affected by V0 and output current will be affected by Vi, which means that there's a direction in which the signal is flowing. It's flowing from input to output. That's what we mean by a unilateral device. So input current is only some function of Vi, and now it could be a nonlinear function also. So this one is here, and so the way we build incremental model is we change Vi. So there is some DC value here, and on top of DC value, we add some small incremental change here, small Vi, and there'll be a corresponding some DC current, plus there would be a small incremental change here. Note that the incremental change could be anything. It could be a triangular waveform, it could be sinusoid, it could be an audio signal, video signal, it could be anything, the small incremental change that we're talking. And so if you're looking for this relationship between small I and small Vi here, and we're looking for under small signal conditions, so which means we can linearize it. So if you're familiar with Taylor series expansion, then you can do a Taylor series expansion around Vi here. Otherwise, basically, the relationship between small I and small Vi would be nothing but II equal to Vi, the first derivative. And so Vi by Ri here, where Ri is given by the first derivative of the function f with respect to Vi at the bias point, at the DC bias point. So that's the incremental model looking at from the input side. The relationship between the incremental change in current and incremental change in voltages, a linear relationship under small signal condition. We have assumed that these changes are small. That's why we are linearizing it, okay? And doing an expansion of this function and keeping only the first term. And the first term has only the first derivative, okay? So from the input port, the device appears as a resistance from this side here. From the output side, I0 is a function of both Vi and V0. And therefore, we can write any, so we want to find out what would be the incremental change in I0 here. So we add here. Now, this could be due to an incremental change in Vi or an incremental change in V0. And then we can do an expansion of this one. Expansion of this one around Vi and V0, the DC values Vi and V0. And so this is the first term. That's the second term. The first order correction here, Vi first derivative evaluated at V0 here, V0 first derivative evaluated at Vi here, and all the other higher order terms which will have Vi square or V0 square and things like that, all those nonlinear terms we are ignoring. So once we ignore that, note that the first term is nothing but the DC current here. So this and this cancels here. So we get I0 equal to Vi, first derivative of function with respect to Vi, and the derivative of function with respect to V0 times V0 here. So we can write this as I0 equal to Gm times Vi. We can define this quantity as transconductance Gm times Vi. And this quantity, we could define it because is the derivative of basically the function F0 or current with respect to voltage here. And so we define it as an output resistance here. So we define it like R0. So from the output side, the incremental change in I0 is related to an incremental change in Vi through this linear relationship under small signal condition and by this one here. So basically this one you can see here could be represented by these two elements. So I0 is the current entering from here. So the first term is GMVI. So we represent it by a voltage dependent current source here. The second term is V0 by R0. So we represent it by R0 here. So the complete model of a three-terminal device, small signal model of a three-terminal device is this one here. From the input side, a resistor Ri. From output side, GMVI and R0 here. So what it says is any nonlinear, any device that is given to you under small signal conditions, it would look like this with some resistor here, some transconductance times Vi here, and some output resistance here. And the reason why this is important for us, we may not get, the time before us is limited in terms of what we can do with transistor amplifiers. But what happens is transistor is a nonlinear element. And normally what we do is we apply some DC voltages and currents to our transistor so that it operates in a suitable region of characteristics. And then So the DC purpose of DC voltages and currents is only to push the transistor into an appropriate region, such that it may be capable of amplification. Then we apply a small signal that we need to be, amplified by the transistor. So when we have amplifier circuit, in general, you will find that you will have DC voltages and currents that are there. And then the quantity of real interest for us is the small signal that we introduce into the amplifier, the signal, audio signal or video signal that we want to be amplified. And therefore, when we analyze amplifier circuits, we need to do a small signal analysis of our amplifier circuit. And therefore, small signal models of the elements are important. And a transistor is nothing but a 3-terminal device, a nonlinear device. And we just said that any 3-terminal nonlinear device model would be like this, a unilateral device. And therefore, even a transistor would look like this. I can describe the transistor under small signal condition by these elements here. A resistor here, a voltage dependent current source, and a output resistor here. All right, so that's the background to the concept of incremental circuit analysis, the small concept of incremental circuit model, and the small signal circuit model. And these, you would see that we've started our discussions related to amplifiers, and you would see that these concepts are important, when we want to analyze and design the amplifier circuits. All right, any questions regarding what we just discussed?